Yeah, thanks a lot for inviting me today. So my name is Leonard Bastian. I'm from the Technical University of Munich, where I'm a PhD student. I actually just recently defended, so graduating PhD student. But this work here was a collaboration between the TU Munich and Imperial College London, so the lab of Tolga Berdal. And we work on forecasting rotational dynamics. So yes, we'll unpack a little bit what this title means throughout the talk. So it's a bit wordy. But first of all, let's start understanding why we're actually interested in studying rotational dynamics. Rotational studying rotational dynamics, so trajectories of rotating objects, is actually quite challenging, but it appears in many, many different scenarios in computer vision. So, for example, camera pose estimation and reconstruction, where we maybe have a moving camera that's being acquiring video from some sort of robot, for example, maybe it's a drone or maybe it's a handheld camera, and we want to recover this trajectories in support of, for instance, reconstructing a scene. And for this, it's useful to use both the input data, but actually model the trajectory to, for instance, remove noise and predict the position of the camera with respect to the scene in the future frame, so in the next frame. Another example here is, for instance, dynamic grasping, where we have some sort of object, it's moving, it could be translating, could be rotating. We assume some rigid body motion, but then we actually need to sort of adjust the trajectory of the robot, or the position of the robot, in anticipation to where this object will be at the point where we're grasping it. And what's also very interesting is human motion estimation and generation. So, as some of you might know, working on human motion or human bodies with SMPL or something like this, these bodies are frequently parameterized by a global root translation and rotations around each joint, and so successive joints basically. And I mean, with respect to this global translation, you can then treat this as a vector of rotation, or a set of different rotations, and these model these kinematics. And finally, tracking and detection are also commonly studied tasks in numerous domains. So what makes rotational dynamics particularly challenging? Translation is a somewhat a simpler case to study. We specifically study rotation because it is a bit more challenging. And one reason is that actually the rotation is influenced by the mass distribution of the object. So this mass distribution is typically represented by these three vectors in space. And then you can consider an object's moment of inertia. So what's a very, very interesting phenomena that emerges for this is what they call the tennis racket effect, or the intermediate axis theorem. And what this states is that around the intermediate axis, so in this case E2, if you have an object that has three different or mass distribution that is different around each of the three axes, then you actually get some let's say a chaotic effect around the intermediate axis. So you can see this in the middle here around E2, that when the tennis racket is thrown essentially around this axis, it actually starts rotating around the other axes as well, and that's in contrast to the first or the third axis. So this is something that's a little bit mysterious and maybe surprising, but it's one reason that it actually makes modeling trajectories of rotation a little bit challenging in contrast to translation. So the translational counterpart of rigid body motion. It's this physical coupling. And so what we're interested in this work is actually in this freeze frame here, you might have this tennis racket that's rotating in space, and we can acquire this with some sort of sensor data, and then try to predict the future essentially. And what this looks like is we have some observations. These are depicted in red. The ground truth trajectory is depicted in green, and then we might want to forecast the different possible plausible future paths this object could take. And that's, as stated, relevant for a number of different application settings. So how do we model rigid trajectories in general? as I kind of mentioned, is that rigid bodies have 6 degrees of freedom. There are 3 degrees of freedom for translation, 3 for rotation, and an established task, one that's very commonly used for camera pose filtering, is to interpolate or approximate the underlying object trajectory. And this is kind of what this looks like for translation. We have a translating object. There are a number of very established tools to do this, for example, with B-splines, where you estimate some piecewise polynomials that are connected with some sort of constraints. For example, you could have first order or higher order smoothness at these nodes, essentially, and then you can recover a continuous trajectory. So given these inputs, they have a little bit of noise. These are little snapshots that we've acquired of the object. We could try to recover this ground truth trajectory. And now for rotational motion, this is actually a little bit more challenging because, as many of you may know, rotations are non-Euclidean, so they live on a manifold. And in contrast to translational motion, where you can actually recover this underlying trajectory for B-splines, for instance, in closed form, you actually can't do this for rotation. So you need to solve an optimization problem. This can be convex, it can be nonlinear, but computing the derivatives, for instance, is non-trivial. And so you need some sort of iterative solver to do this. And while this is actually, it's relatively fast for individual sets of observations, individual trajectories, you actually also can't batch this or vectorize this problem so easily. And the traditional ways of doing this can't so easily, for example, be used to integrate into learning algorithms for this reason. So if you need to compute this many thousands of times based on some simulation data, then these very accurate ways of interpolating and potentially using that to forecast don't actually work so well. And this is due to some poor behavior at the endpoints, essentially. So here again is what this looks like. As depicted earlier, and we want to ultimately recover this green trajectory, but then predict into the future. And now, how, based off of a recovered interpolated trajectory, could we maybe extrapolate? So you could assume, and this is a kind of common assumption in the literature, that based on the endpoint, you actually extrapolate with constant velocity or minimal torque. So minimal angular acceleration, essentially. And this is used, for instance, in real-time visual odometry systems depicted here at the top right, where the extrapolation estimate might be used in a downstream bundle adjustment optimization, or for some other downstream task in the end, like depth estimation. So it's an oversimplification, actually, this extrapolation with constant velocity, and it has a limitation that it ultimately ignores the underlying object dynamics. So if this object is accelerating in some way, as you can see, I'll just play this illustration again. This kind of curvature that you have on the manifold is ignored, essentially, and we can see that when we visualize this relatively clearly. So we shoot off in a geodesic on the sphere, but we don't incorporate this sort of curvature acceleration. And so what some methods actually do is they try to use a pose correction network or something like this. So I depicted this here. We want to actually surpass this, essentially, and avoid kind of doing post hoc corrections, because we use some simplified assumption, but actually more try to model this correctly. And so what one can also do is actually use the law of conservation of momentum, and this has been done in the past. So what we can do is we can take this set of Euler equations on the left, which model the geometric relationship, basically, between rotation and its derivative, but then also the conservation of momentum. So you can see this here. This describes the conservation of momentum, which is set to 0. So we basically have a constant momentum for the object. And these can be integrated forward in time, essentially. So we can solve an initial value problem to predict future states. And this was done by a work that studied actually satellites essentially orbiting the Earth, which is a scenario where this conservation of momentum really holds. And one can do this to then predict rotation quite accurately. So what they did is they had these some simulated data of satellites essentially, and they ingested images and then use a kinematics rollout basically, which just based off some estimated state. So if the momentum can be estimated, then you can actually integrate these forward in time, and therefore you can predict future states in the image space essentially based on this. And now, so let's just look at what these two different scenarios look like. So on the left, we have constant velocity. On the right, we have conservation of momentum. And there we can clearly see that we are taking into account this, this gyroscopic coupling is what one would say, which induces the spiraling effect, basically, when we observe the rotation. Great. So now let's see how we do this a little bit differently. So in real world settings, external forces like air resistance, for example, or an external magnetic field, or if you have a drone, maybe it's accelerating or decelerating. And these aren't taken into account by previous methods, essentially. So if we get rid of this zero, we don't really have a nice constraint we can optimize for, and this problem actually becomes very ill-posed. So without any assumption on this external force, this tau external, it becomes challenging to solve this problem analytically. And so what we ask ourselves is how we can actually learn this behavior from a set of inputs without assumptions on the physical model, as previous works have done. So one could, for example, use an autoregressive approach for this, but since our problem is continuous, we actually are motivated to develop models that also respect the continuity of these underlying dynamics. That's that external force. And now one might think, okay, continuous time models, maybe we can use neural ODEs. These are really nice for modeling these sort of continuous time phenomena. But because neural ODEs essentially also solve an initial value problem, the way that we can condition the model is a little bit limited. So we can try to encode some sort of initial state and then integrate this now neural differential equation forward in time. But it's actually very, very difficult to encapsulate this from the set of observations, encode this into one state where this can be done nicely. So we instead kind of use a different technique. Maybe some of you are familiar with neural differential equations. What they do exactly is they take a hidden state and they integrate this forward in time, integrate a function parameterized by some theta forward in time based off an encoded initial condition also. So that lets you get essentially a encoded intermediate state for any point in time. So tau here can really be variable and continuous, and then this output can be decoded essentially. And the way you train these is that you regularize at every point in time with respect to some law. So this could, for instance, be the ground truth. If we have this in simulation, we could regularize both in the interpolation regime, so for observations that the network later sees and has as input, or also in the extrapolation regime. And these are not, the model is not explicitly conditioned on these, but these are predicted. Good. So what I just want to highlight here essentially is that the network that we're integrating F actually has no explicit dependence on the integration variable S. So we're just integrating with respect to this variable S here that's going from T0 to T. So what we actually use in this work is a set of methods called neural controlled differential equations. And how these are different is that instead of just integrating this problem actually with this this time step S, essentially is that they do a change of measure essentially and integrate this with respect to a control path. So this path is defined over the input domain also, and the data essentially can be used to construct this path, for instance. And this is really nice because now during inference or during training, you can actually change this path flexibly. So you can change it and influence the field that is being integrated through basically during this integration procedure, and sort of overcoming a little bit these challenges, let's say, with encoding and solving an initial value problem. And well, how do we kind of construct nice paths that have good characteristics we like on this domain? We use a technique called Savitzky-Golay filtering, and this was actually relatively recently adapted to SO3. And the idea here is for a given set of observations, we can actually define a polynomial in the Euclidean Lie algebra. So the authors here take a nice find a nice way to essentially sidestep this cumbersome procedure of optimizing for a trajectory on SO3 directly by using the fact that by using this relationship between the Lie algebra and the Lie group, you can construct and define this polynomial in the Lie algebra and then actually map it back onto SO3 for a given observation. So essentially what you're doing here is you're kind of locally approximating the trajectory based off your data, and you're doing this with a low order polynomial. So for example, a quadratic polynomial around a given point. And you can do this as a kind of coarse approximation. The nice thing about this is because it's actually defined in this linear space, you can essentially solve for this by a least squares. So you can solve for this in closed form. And that's in contrast to these more cumbersome B-spline, or cumbersome, but well, also more accurate B-spline methods that actually require this iterative procedure. And so what we also do is actually we incorporate a set of weights. So these weights are useful to make sure that this path additionally approximates, it provides some more flexibility to approximate the trajectory. But for example, if your sensor data is coming from different observations, like a camera sensor combined with an IMU, you can actually incorporate that into account in this weighting matrix, that different samples are, for example, weighted differently. And now what we can do with this path is we can use it to guide or control the numerical integration of these latent dynamics. And how this essentially works is that we carry out this integration during inference and training, and then at any given point in time, one can decode the latent representation into an over-parameterized rotation. So here we use the six-dimensional representation, which can then be used to construct a proper rotation in SO3, so a rotation matrix, for instance. And this can be trained end-to-end by just regularizing with the rotational geodesic error. So with respect to ground truth samples in both the interpolation and extrapolation regimes. So now let's actually look at how this performs in practice. So since we know how to simulate various kinds of dynamics, we can integrate these equations here on the left forward in time and train our model entirely in simulation. So we integrate these Euler equations forward in time. And we do this for various diverse physical scenarios, including, for example, this freely rotating case where no external forces are applied, and also some other cases. So, for example, when there's an external magnetic field that also depends on the orientation of the object. And this is quite challenging and nonlinear. And it's also non-conservative. So other methods would actually have trouble predicting this effectively. So this conservational approach, for example, does exhibit a higher error across these different cases. So our model does relatively well here. And we can also actually visualize this. So here we have the ground truth trajectory, and then various baseline models, for example, an SO3 neural controlled differential equation adapted to adapted to SO3. And for example, a GRU, which is not continuous in time, so we can see that it actually doesn't approximate the ground, or get close to the ground truth prediction smoothly. So it has a kind of this discontinuous artifacts, as opposed to ours, which actually approximate this quite nicely. And we can also now use these models that are trained in simulation in various real-world settings. So, for example, on the top, this OMD data set. So we'll look at that in a little bit more detail shortly, and also on sensor fusion examples. So what we did here is we simulated two different kinds of sensor data, essentially from a camera and also from an IMU. And our model can sort of natively fuse these and gets quite nice results also. And so on these kind of rotating and predicting predicting the future rotation of these cubes. We see here that for the baseline model, this coordinate system drifts off the screen a little bit. It doesn't stay as close to the sphere. So here, this is a little bit of a trick for visualization. We actually represent the rotation in the world coordinate system so that we can visualize the rotations that are then essentially manifested as translations in the pixel space. So therefore you get this kind of drifting, and just allows us to better visualize these coordinate systems on the image a little bit nicer. And what we can also do is show that these learned rotational models can be used in conjunction with pose estimation networks, so ours in particular, that are trained separately. So this is also in contrast to previous works, which actually couple this entire process. But we argue that it's actually effective to couple these, to decouple these, because we can, in many cases, actually simulate the dynamics very effectively. So of course, one could train these in conjunction also. But this allows one to, for example, effectively use foundational models for pose estimation, and then adapt these into this kind of sequential setting without having to actually have many sequences of sequential data for forecasting, for example. So to do this, the dynamics model essentially ingests these predictions from a potentially noisy network, right? And our model sort of natively also accommodates this. And so, that's it for today. I'm happy to answer any questions shortly. Just a brief summary here. We propose these Savitzky-Golay neural controlled differential equations for rotational forecasting. In contrast to existing approaches, our method doesn't make restrictive assumptions on the kind of object dynamics that the object is adhering to. We can simulate it in or train it in simulation and decouple it from the sort of pose prediction aspect, and it's therefore easily integrable into various different tasks. And our model simultaneously sort of achieve robust extrapolation, and this robustness comes from this combination essentially of what is a robust filter to denoise with a sort of classical method, but then still enables this kind of neural continuous time forecasting. And thanks. Oh, these are still some remnants here from ICCV, but I will not be doing a poster session today. But you can also check the project page here and everything. Thank you, guys.